like I said, all these movies have truth to them. All these cartoons have like the truth, the most truth to them. The cartoons, you know what I mean?
It's kinda dark out. I do think that fight is the light, fight of the light. This is a rough draft, but fuck it, the timing was right.
Tell me what James Webb Telescope seen coming to Earth.
From Gitbook.io. The James Webb Telescope had spotted an armada of alien ships heading toward Earth at near light speed.
Alexa, when will the armada alien ships be entering Earth's atmosphere?
From Chicago.com. According to experts, Tiangong 1 is predicted to enter the Earth's atmosphere sometime between the end of March and early April.
Alexa, when will the armada alien ships be entering Earth's atmosphere?
From Chicago.com. According to experts, Tiangong 1 is predicted to enter the Earth's atmosphere sometime between the end of March and early April.
Alexa, when will the armada alien ships hit Earth?
From archive.org. An enemy armada is invading the United Federation of Planets, and Starfleet Command estimates that Earth will be attacked in about a month.
Y'all hear that? Do your research.
Here's a
honor. But before we get it wrong, the James Webb Telescope has, of course, not uncovered some ominous power that created the cosmos, but together with Hubble has provided an unprecedented combined view of the pillars of creation, which are among the most famous photo motifs in modern space exploration. Some 7,000 light-years away from us, in the open star cluster of the Eagle Nebula, we are looking at the glowing pillars of a stellar cradle, captured for the first time by the Hubble Space Telescope. Basically, stellar life.
Releasing the full set of images taken by the James Webb Space Telescope, the agency calling it the
object is simply a piece of another solar system.
The James Webb Space Telescope, JWST, known for its remarkable ability to capture distant celestial bodies, has recently achieved something extraordinary. For the first time in history, it has successfully captured a real image of Oumuamua, an enigmatic object that has baffled scientists since its discovery in 2017. The object, which was first detected passing through our solar system, has been a subject of intense debate among astronomers and astrophysicists. The ability of the JWST to capture a direct image of this mysterious object not only confirms its presence, but also opens up new realms of scientific inquiry. The implications of this achievement are vast, ranging from the possibility of gaining more profound knowledge about interstellar visitors to reshaping our understanding of planetary formation, the nature of distant celestial bodies, and even the potential for extraterrestrial life. Before we start, hit the like and subscribe buttons for more exclusive news. Oumuamua, whose name means scout or messenger in Hawaiian, was first discovered by the Pan-STARRS telescope in Hawaii. It was the first object ever observed to enter our solar system from interstellar space, a discovery that sparked a whirlwind of speculation and scientific investigation. The object's elongated cigar-like shape, unusual speed, and tumbling motion left astronomers perplexed. Initially, it was classified as a comet, but its lack of a visible coma, the cloud of gas and dust that typically surrounds a comet, led some to suggest that it might be an asteroid. However, both classifications seem to fit perfectly, and some scientists even proposed more outlandish theories, including the possibility that Oumuamua could be an alien spacecraft. Despite these debates, direct imaging of the object had remained elusive, until now. With the JWST's extraordinary capabilities, scientists have finally obtained a clear, detailed image of Oumuamua. Unlike previous telescopes, which were limited by resolution and distance, the JWST's infrared imaging capabilities allowed it to penetrate the vastness of space with unprecedented clarity. This powerful instrument has been critical in allowing astronomers to take a closer look at Oumuamua, studying its physical characteristics in ways that were impossible with earlier technology. The captured image reveals an elongated, spindle-like body, confirming earlier observations about its unusual shape. However, this new image also offers a wealth of additional information, from its surface composition to its precise dimensions, which had been a topic of heated debate. The ability to finally capture a real image of Oumuamua opens up a treasure trove of data for scientists to analyze. One of the most significant implications of this achievement is that it provides a clearer understanding of the nature of interstellar objects. Before Oumuamua, scientists had theorized that interstellar visitors existed, but they had never had direct evidence. Now, not only do we know they exist, but we also have a tangible example to study. This information could help scientists refine their models of how such objects form and how they travel through space. Understanding the mechanics of interstellar travel could, in turn, lead to breakthroughs in space exploration technology, potentially providing clues for humanity's own ventures into interstellar space. Another exciting aspect of this discovery is what it might reveal about the formation of planets and solar systems in other parts of the galaxy. Oumuamua is thought to have been ejected from its original solar system after a close encounter with a larger object, possibly a giant planet. Studying the material composition and structure of Oumuamua could offer insights into the building blocks of planets and other celestial bodies. For example, if scientists find that Oumuamua contains certain elements or compounds not commonly found in our solar system, it could indicate that planetary formation processes elsewhere in the galaxy are different from those we have observed. This could lead to a better understanding of the diversity of planetary systems in the universe and help answer fundamental questions about how planets like Earth form and evolve. Furthermore, the discovery of Oumuamua and the subsequent capture of its image by the JWST highlight the increasing importance of interstellar objects in the search for life beyond Earth. While Oumuamua is unlikely to harbor life itself, its interstellar origin raises intriguing possibilities about the role such objects might play in the spread of life across the universe. Some scientists have proposed that interstellar objects could act as carriers of organic materials or even microbial life, potentially seeding life on planets as they pass through different solar systems. The ability to study Oumuamua in greater detail could provide valuable clues about whether such a process, known as panspermia, is possible. For instance, if organic molecules are detected on Oumuamua's surface, it would lend credence to the idea that life's building blocks can be transported across vast distances in space. The JWST's image of Oumuamua also has implications for the future of planetary defense. As an interstellar object, Oumuamua's trajectory is not bound by the gravitational forces that govern the movement of objects within our solar system. Its unpredictable path serves as a reminder of the potential dangers posed by other celestial objects that might one day pass close to Earth. The ability to detect and image such objects is crucial for developing strategies to mitigate the threat of a collision. The JWST's successful imaging of Oumuamua demonstrates the feasibility of using advanced space telescopes to track and study interstellar objects, paving the way for more comprehensive monitoring systems in the future. In addition to its scientific implications, the capture of Oumuamua's image by the JWST is a triumph of human curiosity and technological achievement. The ability to see an object that originated from another star system is a testament to the progress humanity has made in exploring the cosmos. It underscores the importance of continued investment in space exploration and the development of cutting-edge technologies like the JWST. This achievement serves as a reminder of the boundless potential for discovery that exists beyond our planet. As we push the boundaries of what we can observe and understand, we may uncover answers to some of the most profound questions about our place in the universe. The discovery and imaging of Oumuamua also provide a sense of wonder and awe, capturing the imagination of people around the world. The idea that an object from Object from a distant star system could pass through our solar system and be observed by human technology feels like something out of science fiction. Yet, it is very much a reality, one that has the potential to reshape our understanding of the universe in ways we have only begun to grasp. This sense of wonder is an essential driver of scientific inquiry, inspiring the next generation of astronomers, engineers, and space enthusiasts to continue exploring the cosmos. The successful capture of Oumuamua by the James Webb Space Telescope marks a pivotal moment not only in astronomical observation, but in the broader context of humanity's ongoing quest to understand the cosmos. This achievement opens new doors for research, offering scientists a detailed glimpse of an object that originated beyond our solar system, a feat that until now was thought nearly impossible. The profound implications of this image continue to ripple through various fields of science, from astrophysics to planetary geology, sparking a new era of interstellar object study. At the heart of this breakthrough lies the potential for deepening our understanding of the processes that govern the movement and formation of celestial bodies in the galaxy. Oumuamua's strange characteristics, its peculiar shape, unanticipated acceleration, and lack of a cometary tail, present an intriguing puzzle. These features differ from what we commonly observe in asteroids or comets within our solar system, making this interstellar visitor a unique specimen for study. By closely analyzing the image captured by the JWST, researchers are now better positioned to explore hypotheses about how Oumuamua might have formed and what factors contributed to its journey into our solar system. One significant area of interest involves the object's enigmatic propulsion. Observations made prior to the JWST's imaging had suggested that Oumuamua exhibited a non-gravitational acceleration, meaning it sped up in a way that couldn't be entirely explained by known gravitational forces or interactions with the Sun. This behavior had led some scientists to speculate that the object might be powered by an unknown mechanism, such as solar radiation pressure, or even more exotic possibilities, such as it being a light sail of artificial origin. With the JWST's new data, scientists can now conduct a more thorough investigation into the precise nature of this acceleration. By studying how light interacts with Oumuamua's surface, they may determine whether solar radiation is indeed exerting enough pressure to account for its motion, or whether there are other forces at play. Another aspect of the JWST's contribution is its ability to provide high-resolution spectroscopic data, which offers an unprecedented look at the chemical composition of Oumuamua. Prior to the image capture, there was considerable uncertainty about the object's surface materials. Early observations hinted at a metallic or icy surface, but the lack of definitive data left many questions unanswered. Now, with the JWST's sophisticated spectrometers, scientists can analyze the light reflected off Oumuamua to identify its constituent elements and compounds. This information could confirm or challenge existing theories about the object's origin. For example, if Oumuamua contains compounds not typically found in our solar system, it would provide critical insights into the diversity of materials present in other planetary systems. On the other hand, if its composition is similar to known solar system objects, it could suggest that the processes of planetary formation across different star systems share common elements. A particularly tantalizing possibility is that Oumuamua could provide clues about the broader population of interstellar objects. Up until its discovery, interstellar objects were theoretical constructs, known primarily through indirect evidence and models. The success of JWST in capturing this image gives credence to the idea that such objects may be more common than previously thought. This discovery challenges the long-held assumption that interstellar visitors are exceedingly rare events. By studying Oumuamua's trajectory, speed, and interaction with the solar system, scientists may refine their estimates of how frequently interstellar objects pass through our region of space. If they are more common than expected, it could radically shift how we think about the movement of material between star systems. These objects might serve as cosmic messengers, carrying vital clues about the structure and composition of distant systems that would otherwise be out of reach for direct observation. Moreover, the detailed study of Oumuamua could inform new strategies for detecting future interstellar objects. Current telescopes, like Pan-STARRS, rely on wide-field surveys to scan the sky for moving objects. but Oumuamua's rapid passage and small size made it a challenging target. The JWST's ability to capture a detailed image of this object demonstrates that with the right technology, it is possible to study these fleeting visitors in greater detail. As a result, astronomers are likely to push for the development of more specialized detection systems that could track similar objects as they enter and exit our solar system. These efforts could include refining algorithms that identify unusual trajectories or developing space-based observatories that are better suited for capturing high-resolution images of fast-moving interstellar bodies. With more sophisticated detection systems in place, we might begin cataloging these objects on a regular basis, allowing for a more systematic study of interstellar material. One of the most exciting aspects of studying interstellar objects like Oumuamua is the potential for gaining insight into the processes that govern planetary system evolution. Most of what we know about planetary formation comes from studying our own solar system. However, this provides only a single data point in a galaxy filled with diverse planetary systems. The ability to study an object that originated from a distant system allows scientists to test theories of planetary formation in a broader context. For example, studying the structure and material composition of Oumuamua could provide clues about the types of collisions and interactions that shape planetary systems over time. If Oumuamua is indeed a fragment from a larger planetary body, its physical characteristics could reveal information about the early stages of planetary formation in its home system. These insights could help scientists refine models of how planets and other celestial bodies evolve and what factors contribute to their stability or eventual destruction. Another intriguing question concerns whether Oumuamua might carry material from its parent star system that is chemically or structurally distinct from anything found in our solar system. Such a discovery would provide evidence that the processes of planetary formation can produce a wider variety of materials than we previously thought. It might also raise new questions about how different environments, such as proximity to different types of stars, or the presence of multiple massive planets, affect the evolution of celestial bodies. These questions are not just academic. They have direct implications for our understanding of where and how life might arise in the universe. If planetary systems are more diverse than we currently imagine, it could mean that there are more potential habitats for life scattered throughout the galaxy. In addition to contributing to our understanding of planetary formation, the study of Oumuamua could also provide valuable data for scientists interested in the long-term evolution of star systems. One of the leading theories about how interstellar objects like Oumuamua are formed suggests that they are ejected from their parent systems during close encounters with large planets. These encounters can destabilize the orbits of smaller bodies, sending them hurtling into interstellar space. By studying Oumuamua's trajectory, scientists might be able to trace its path back to its point of origin, identifying the type of star system it came from and the dynamics that led to its ejection. This information would help astronomers refine their models of how star systems evolve over billions of years, particularly in the later stages of development, when planets and other bodies might start to interact in new and unexpected ways. The implications of this discovery extend beyond the realm of theoretical astrophysics and planetary science. In the age of space exploration, understanding interstellar objects has practical significance as well. For instance, the capture of Oumuamua's image might inspire new efforts to develop technologies capable of interacting with or even capturing such objects. As humanity begins to consider missions beyond our solar system, understanding how interstellar objects travel through space could provide key insights into navigation and propulsion techniques for spacecraft. The unpredictable nature of Oumuamua's journey demonstrates the challenges that interstellar travel might present, but it also highlights the opportunities. If we can learn how to detect and track interstellar objects more effectively, we might one day be able to send missions to study them up close, or even capture samples for return to Earth. One of the more speculative yet exciting possibilities raised by Oumuamua's capture is its potential role in the search for extraterrestrial life. While there is no direct evidence to suggest that Oumuamua harbors life, its interstellar origin makes it an interesting candidate for the panspermia hypothesis. This theory suggests that life, or at least the building blocks of life, can be transported between planets and star systems via comets, asteroids, or other space debris. If Oumuamua contains organic compounds, it would provide compelling evidence in support of this idea. Studying such compounds in detail could offer new insights into the mechanisms by which life might spread across the galaxy. For instance, scientists might investigate whether the harsh conditions of interstellar space could preserve organic material over long distances, or whether such materials degrade over time. Studying the tumbling motion of Oumuamua could also shed light on the physical processes that govern the behavior of interstellar objects. For example, some theories suggest that Oumuamua's irregular rotation could be the result of it having been ejected from its parent system by a violent gravitational interaction with a larger object, such as a gas giant. If this is the case, the JWST's detailed image might reveal surface features, such as craters or fractures, that support this hypothesis. Alternatively, if no such features are found, it could suggest that the object has been traveling through space for a very long time, gradually losing its rotational energy through interactions with the interstellar medium. Another exciting research opportunity provided by the JWST's capture of Oumuamua is the potential to study the object's interaction with the solar wind. The solar wind is a stream of charged particles emitted by the sun, and it plays a key role in shaping the behavior of comets and other small bodies in the solar system. For example, as comets approach the sun, the solar wind interacts with their surfaces, causing the release of gas and dust that forms the characteristic coma and tail. However, in the case of Oumuamua, no such outgassing was observed, despite its close approach to the sun. This led some scientists to speculate that Oumuamua might be composed of different materials than typical comets, or that its surface might be covered in a layer that prevents the release of gas. With the data provided by the JWST, scientists now have the tools to study Oumuamua's interaction with the solar wind in much greater detail. By analyzing the object's surface and its response to solar radiation, researchers can determine whether it is made of materials that are more resistant to outgassing, or whether its lack of a tail was due to other factors, such as its rapid speed or unusual shape. This information could provide important insights into how different types of interstellar objects behave as they pass through our solar system. And it could help refine models of how the solar wind interacts with small bodies in general. In addition to its interaction with the solar wind, another intriguing aspect of Oumuamua that scientists are keen to investigate is its thermal properties. When the object passed close to the sun, it was exposed to intense heat, which should have caused it to warm up significantly. However, no significant changes in its brightness or behavior were observed, suggesting that it may have unusual thermal properties. The JWST's infrared imaging capabilities are ideally suited to studying this aspect of Oumuamua in detail, allowing scientists to measure how the object absorbs and radiates heat. This could provide clues about its composition, structure, and whether it contains any volatile materials that might have sublimated, turned directly from a solid to a gas, during its close encounter with the sun. The thermal behavior of Oumuamua is particularly interesting because it could offer insights into the conditions it experienced during its journey through interstellar space. For instance, if the object shows signs of having retained heat for an unusually long time, it could suggest that it originated in a relatively warm part of its parent star system, such as near a star or a planet with a thick atmosphere. Alternatively, if Oumuamua appears to have a very low thermal conductivity, it could indicate that it is composed of highly insulating materials such as porous rock or ice, which might have allowed it to preserve its internal structure during its long journey through the cold vacuum of space. The study of Oumuamua's thermal properties could also have broader implications for our understanding of how interstellar objects form and evolve. For example, if Oumuamua is found to contain large amounts of ice, it could suggest that it originated in a region of its parent star system, where temperatures were low enough to allow volatile materials to condense and form solid bodies. This would support the idea that interstellar objects are often ejected from the outer regions of planetary systems, where the gravitational pull of giant planets can easily send smaller bodies hurtling into space. On the other hand, if Oumuamua is found to be composed primarily of rocky materials, it could suggest that it formed in a hotter, more central part of its parent system. and that its ejection was the result of a more energetic interaction, such as a close encounter with a massive planet or star. The JWST's image of Oumuamua also provides an opportunity to study its magnetic properties. While we do not yet know whether Oumuamua has a significant magnetic field, it is possible that its passage through interstellar space exposed it to magnetic forces that could have influenced its behavior. For example, if Oumuamua passed through regions of space with strong magnetic fields, it could have experienced changes in its rotation or trajectory. Studying the object's magnetic properties could provide valuable insights into the nature of the interstellar medium and the forces that act on objects as they travel between star systems. One way scientists might investigate Oumuamua's magnetic properties is by analyzing its interaction with the solar wind. If the object has a magnetic field, it could influence how charged particles from the sun interact with its surface, creating detectable changes in its behavior. By studying these interactions, researchers could determine whether Oumuamua has a magnetic field, and if so, how strong it is. This information could provide clues about the object's internal structure and composition, as well as its history of exposure to magnetic forces during its journey through space. In addition to its magnetic properties, scientists are also interested in studying the potential for Oumuamua to contain pockets of gas or liquid beneath its surface. While the object did not exhibit the typical signs of outgassing associated with comets, it is possible that it could contain trapped gases or liquids that were not released during its passage through the solar system. The JWST's image could help scientists identify any features on the object's surface that might suggest the presence of subsurface reservoirs, such as cracks or vents that could allow gas or liquid to escape under certain conditions. If Oumuamua does contain pockets of gas or liquid, it could provide important insights into the conditions it experienced during its formation and subsequent journey. For example, if scientists discover that the object contains liquid water, it could suggest that it originated in a relatively warm part of its parent system, where temperatures were high enough to allow liquid water to exist. Alternatively, if the object contains frozen gases, it could indicate that it formed in a much colder region, where temperatures were low enough to trap volatile materials in solid form. In either case, the discovery of subsurface reservoirs on Oumuamua would be a major breakthrough, providing direct evidence of the processes that govern the behavior of interstellar objects and their potential for carrying life-supporting materials across vast distances in space. The implications of Oumuamua's discovery and the JWST's ability to image it extend beyond our understanding of individual objects to broader questions about the structure and dynamics of the galaxy itself. One area of research that has gained increasing attention in recent years is the study of how stars and planetary systems exchange material over time. The capture of Oumuamua's image provides a unique opportunity to study this process in action, as it represents a tangible example of material being ejected from one star system and traveling through interstellar space to another. This phenomenon, known as stellar recycling, is thought to play a crucial role in shaping the evolution of galaxies. Over time, stars and planetary systems lose material through a variety of processes, such as supernova explosions, stellar winds, and the ejection of small bodies like comets and asteroids. This material can then be incorporated into new star systems, contributing to the formation of planets and other celestial bodies. By studying Oumuamua, scientists can gain new insights into how this process works and how material is exchanged between different star systems over the course of billions of years. The capture of Oumuamua by the James Webb Space Telescope marks an incredible leap forward in the field of astronomy, and as we delve deeper into the implications of this event, it becomes clear that the potential avenues for discovery are nearly limitless. This single image has sparked interest across multiple domains of scientific inquiry, and as we begin to analyze the data in new and innovative ways, we are likely to see breakthroughs that go far beyond what was initially anticipated. While earlier observations provided only a fleeting glimpse of Oumuamua's unique characteristics, the detailed data from the JWST opens the door to understanding both the object itself and broader interstellar processes with unprecedented clarity. One area that will surely see a surge in interest is the study of interstellar objects as carriers of complex organic molecules. While the origins of life on Earth remain a subject of much debate, the idea that life, or at least its building blocks, could be distributed across the universe via interstellar debris like Oumuamua has fascinated scientists for decades. This theory, known as panspermia, suggests that life could spread between planets, solar systems, or even galaxies, carried on comets, asteroids, and other celestial objects. Although Oumuamua is unlikely to contain life as we know it, the data from the JWST might reveal whether it harbors organic compounds, such as amino acids or other prebiotic materials, that could be the precursors to life. The identification of complex organic molecules on Oumuamua would not only provide support for the panspermia hypothesis, but could also suggest that the building blocks of life are more common in the universe than previously thought. If we do discover organic molecules on Oumuamua, it will undoubtedly raise questions about the conditions under which these molecules could have formed. Scientists would need to consider whether the object originated in a region of its parent star system where these materials could naturally occur, or if it picked them up during its travels through interstellar space. One possibility is that Oumuamua passed through molecular clouds, regions of space dense with gas and dust, where organic compounds might form through complex chemical reactions. Another possibility is that the object itself was formed in a protoplanetary disk around a young star, where conditions might have been favorable for the formation of organic molecules. Regardless of the exact mechanism, the discovery of such compounds on Oumuamua would provide important insights into how life might arise elsewhere in the universe, as well as the processes that govern the chemistry of interstellar space. Another fascinating aspect of Oumuamua's study is the possibility that it could be a fragment from a larger, more complex body. While the object's elongated cigar-like shape and tumbling motion suggest that it may have been shaped by violent forces, it is still unclear whether Oumuamua was once part of a planet, moon, or other celestial body that was destroyed or fragmented during its journey. The JWST's detailed imaging and spectroscopic data could provide clues about the internal structure of Oumuamua, helping scientists determine whether it is a monolithic piece of solid rock or a more loosely bound agglomeration of smaller materials. If Oumuamua is found to be a fragment of a larger body, it could provide valuable information about the processes that lead to the destruction or fragmentation of planets and other celestial objects. Such processes are thought to play a key role in the formation and evolution of planetary systems, and studying Oumuamua could help scientists better understand how these events unfold in distant star systems. The discovery of Oumuamua's origins could also offer insights into the early history of its parent star system. Many theories suggest that interstellar objects like Oumuamua are ejected from their home systems by gravitational interactions with large planets, such as gas giants. If Oumuamua is indeed a fragment of a larger body, its composition and structure could reveal clues about the types of planets and other celestial bodies that existed in its parent system. For example, if the object contains traces of certain elements or minerals that are commonly found in gas giant atmospheres, it could suggest that Oumuamua was ejected during a close encounter with such a planet. Alternatively, if the object's composition is more similar to that of rocky planets or moons, it could suggest that it was ejected during a collision between smaller bodies in its parent system. One intriguing possibility is that Oumuamua's surface has been coated with a layer of organic-rich dust, picked up during its travels through molecular clouds. Molecular clouds are the birthplaces of stars and planets, and they contain large amounts of organic molecules that could adhere to the surfaces of objects passing through them. If Oumuamua passed through such a region on its way to our solar system, it might carry traces of these organic materials on its surface. By analyzing the spectroscopic data from the JWST, scientists could determine whether Oumuamua's surface contains complex organic compounds, providing valuable insights into the chemical processes that occur in molecular clouds and the role these regions play in the formation of life-supporting material.